So what we're going to do now is talk about ways to implement a concurrent collector. And then we're going to show some code related to the concurrent collector. And then we're going to go through a couple of example programs that use the concurrent collector to do various kinds of interesting things. So this topic really kind of belongs back in the parallel streams discussions, but hopefully it's interesting to you to see kind of how it all fits together. So if you take a look at the Java collectors utility class, if you remember, utility class is a class that has static methods, typically a private constructor, it's usually final, and it has no non-static state or fields in it. It provides a number of factor methods that make non-concurrent collectors. So toList, toSet, toMap, toCollection, and so on and so forth. There's also some factor methods that we didn't really talk much about in this course that make collectors that implement concurrent map. So for example, you can use the toConcurrent map factor method in the collectors class to make a concurrent hash map to be the map that's the concurrent map, what's called the mutable result container to make you could use the toConcurrent map factor method to make a concurrent skip list map, and so on and so forth. However, there are no predefined concurrent collectors provided by Java that create sorted maps. So you might want to, for example, create a concurrent collector that will have its results in sorted order when it gives back the map as the result of doing collect. And there's a whole bunch of reasons why you might want to do this, and I'll show you some examples later to demonstrate why you might want to do that. But that's not a feature that's provided with Java out of the box. And one reason for that is that if you think about what it would take to implement a concurrent tree map, that would be a very difficult thing to do. It would not be efficient. In contrast, concurrent hash map can be implemented very efficiently because there's no need to order the keys that are in the map. So you can do all kinds of clever things. And in fact, the concurrent hash map does all kinds of very clever things. So this is the itch that we're going to be scratching in this discussion. So to overcome this limitation, I created something I call concurrent map collector, which implements the collector interface, and it's designed to overcome this omission with the Java class library. So it supports the ability to make different kinds of maps that could very well be ordered if you so choose. And the way that this is done is through something called a supplier parameter that's passed to the toMap factor method, which we'll talk about here in a minute. So before we do that, let's just go through the generic types that concurrent map collector defines. So there are 4 of them. And you can see the source code here. We'll take a look at the source code later to illustrate how everything works. So the first type of generic parameter is the type of objects that are available from the stream. So you remember, a collector collects stuff from a stream, and T is the type of elements in the stream. So for example, if you've got a stream of simple immutable entries or GCD params or whatever, these are things that you would need to be able to have in your stream that you want to convert into a map somehow. And very oftentimes, though by no means not always, these types in the stream may actually have multiple fields that you can use for key value bindings. Speaking of key value bindings, another parameter is key, or K, which is the type of key used in the map, which could be double or string or integer or whatnot. Then there's V, that's the type of value used in the map, which could be search results, integer, string, double, whatever. And then finally, the 4th parameter is M, which is the type of map that's returned from the collector, which could be concurrent hash map, could be tree map, could be linked hash map, and so on and so forth. And notice that there's no requirement that the type of map returned from the collector actually implements concurrent map, which is the requirement that is in force if you use the toConcurrent map factor method on the Java collectors class, utility class. Now, under the hood, as we'll see when we get into the implementation discussion, the concurrent map collector uses concurrent hash map internally. And it does this on purpose because concurrent hash map is very heavily optimized for concurrent updates from parallel streams. And we'll see how that plays out in just a minute when we get to the examples. The way you make one of these things is by using the toMap factor method, which is a static method that's going to create a new instance of concurrent map collector that will be parameterized by various Java functional interface objects, such as a function called a key mapper that maps the type T to a key, another function called value mapper that maps the type T to a value, something called merge function, which is a binary operator that's going to be used if you have two keys that collide to identify what to do with the value in that case. And then the final parameter, which is a supplier, is the kind of the factory object that creates the appropriate map that will be returned from concurrent map collector. So given that, there's then 5 key methods that are defined, and these are the 5 methods you pretty much always define if you're making yourself a collector. So the first method is the characteristics method. This is what provides the additional information or metadata that's used to optimize the collector. And this particular collector is unordered because it's a map, so we don't care about ordering. And it's also concurrent because it's going to be used, it's intended to be used primarily by parallel streams. You could use it for sequential streams, but it's kind of overkill for that. And as a consequence of making the characteristic concurrent enabled, it means that the accumulator is called concurrently on the concurrent hash map, which is the mutable result container. And that means that the concurrent hash map methods are all synchronized, which is, of course, the case. And they're not just synchronized, they're really cleverly synchronized so that if you have keys that map to different buckets in the hash table, there's no contention. If you have keys that map to the same hash element, then if they're just being inserted, then they have clever tricks to try to avoid overhead there as well. So they do a lot of things to really speed up performance in a concurrent environment. And the way you set this, as you probably already know, is you use something like enum set of, and you pass in the types of enumerated literals you want in order to be able to make this particular set, which is an unmodifiable set, so it can't be changed. Then the next method we have here is the so-called supplier. And this returns a supplier that acts as a factor method to generate an empty mutable result container. So it's going to be the thing that makes the result container we're going to use in the concurrent collector, which in this case is concurrent hash map. It says hash set, but it should say hash map. And then the accumulator returns a by consumer that adds a new element to the existing concurrent hash map, which is used as the one and only mutable result container for all the different threads that might be running in a parallel stream. That's what makes it a concurrent map, if you recall. And here's what the accumulator implementation looks like. It returns a by consumer, and what it does is the by consumer it returns takes a map, which in this case is a concurrent hash map, of course, of type map KT, and an element of type T, and then it goes and it says map merge. Then you basically take the element, you apply the key mapper to it, you take the element, you apply the value mapper to it, and that creates the key and value associated with that element. And then you put that into the map using the merge function. And as again, we'll see later when we see the application of this, the merge function is basically what's used in order to deal with the fact that maps can't have duplicate keys. So if you have 2 keys that appear that are the same value, then the map merge function decides what to do about that. And you can provide the merge function to give an indication of what you want to have done there. Concurrent hash map's merge method is also very efficiently synchronized, like all the methods in concurrent hash map. There's also a combiner, which returns a binary operator that merges 2 result containers together. So if you have 2 maps that need to be merged, then you just put the contents of one and merge it with the contents of the other. And this, you might think at first glance, you don't need this method because this is a concurrent collector, but because of some things we do, we actually do need to have this method, and it gets called one time, and we need it to be there. And then the final method here, which is really the most interesting one, is the one that's called the finisher. And it returns a function that converts the concurrent hash map to the final result type. And let's take a look and see what it looks like, because it's really interesting. What finisher does is it takes the concurrent hash map that it's got as the mutable result container, and then it uses the map supplier that was passed in the toMap factor method to make the appropriate type of map that the user wants. And if the type that's returned is an instance of concurrent hash map, in other words, if this is a concurrent hash map, then we're just going to return the current map because we don't need to do any conversions. We've already got it in the format that the user has requested. However, more interestingly, if the user has given a different kind of map, like, for example, a tree map or a linked hash map, then we go ahead and we take the contents of the current concurrent hash map and we put them into the new map, whatever that type of map was. And then we return the new map. So data is only copied if the map M is not a concurrent hash map. So that's just a clever little optimization to make things work efficiently when we just need to use this as a concurrent hash map. So we're going to go ahead and take a look at an example that illustrates how all this stuff works in just a minute.